everybody doing? Hello, everybody. I'll wait maybe one more minute. Hi, how's it going, Torland? You're doing food? You're doing good. I'm doing good too. Happy it's Friday. Happy it's Friday. How about you guys? You forgot it's Friday. All the days blend together a little bit throughout this quarantine stuff. Even though it's starting to relax. We're getting back to some level of normal. I'm excited about that. Not happy for those who work in weekends. Do you work weekends, Kevin? Hey, you're making money though. You guys ready to get started? How was the homework? How did that treat you guys? I got a couple questions about the root locus stuff, but it seemed like people were figuring it out. It's just a matter of defining those polynomials for the characteristic equation. Easier than previous homeworks. Yeah, the hardest homework so far, probably homework 2, right? This one, yeah, I agree. This one was a little more straightforward. What is the goal of the stream? I'm French, and I don't know what lecture means in English. So this is a summer class. We're at the University at Buffalo in New York. And this is a university class in mechanical engineering. And it's about system dynamics. You can tune in if you want. All right, everybody. We're gonna talk a little bit more about second order systems today, and we're gonna use the root locus. Now I picked a specific second order system that I can show you a real life demo of today, hopefully. It's another circuit, and it's going to be a series RLC circuit. Maybe I can give you a little preview. Oops. It's going to look a lot like the RC circuit, almost identical. Wait, I want to go over here. We have this capacitor, and this guy right here, it looks like a resistor, but it's actually an inductor. And the inductor is what makes this, well, combined the inductor and the capacitor, that makes this a second order circuit. So we'll go through all the details of that. Let's talk about what an inductor is first. So what this is, it's a coil of wire. So if you draw it, you know, you have, I mean, the inductor I have here, you can't really see it, but you take a wire and then you just like loop, 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 loop. You could do this by wrapping a piece of wire like around a pencil or something in a circular pattern. And that's basically what an inductor is in a circuit. So when it turns out when you coil wire circularly like this and you run current through it, so when current flows through it, the inductor creates a magnetic field. So if you've ever heard of an electromagnet, a magnet that you turn on by activating it with power, there's likely some inductor involved. So pretty cool. Just running current through a coiled wire like this creates a magnet. You could probably try this on your own. Don't shock yourself though. It creates a magnetic field. Now, this magnetic field resists changes in electrical current. So say you're, I don't know, you have a milliamp of current just flowing through this circuit. An inductor is going to resist any change in that magnetic current. I mean, in the electrical current. So it's going to take extra energy injected into the system if you want to adjust that current. So just like we did with resistors and capacitors, we're going to define how this functions in a circuit with how voltage rises or drops going across the element. And it's going to be pretty much the same as resistors and capacitors. So let's say we have points A and B, and this is our inductor. And usually the symbol for an inductor is a capital L. And let's define current going this way from A to B. So if we take the voltage from A to B, and once again, this just means the voltage on the right side minus the voltage on the left side. This is going to be, we'll call it minus VL. So basically what this is saying is you're going to lose voltage as you cross an inductor in the direction of current. So just to be complete, if we were taking a loop from the other direction, well, we would gain voltage. Now we'll get a little more detail about this VL term using the element equation. So this is what we call the element equation for an inductor. Another fancy word for this equation, I believe, is the constitutive or constitutive equation, however you say that. But the time derivative of the current going through the inductor is equal to 1 over L times that voltage difference across the inductor. Or if we use that dot notation for the time derivative, you could say I dot is 1 over L VL. It's a little weird using the dot notation with I for current because you have like, the dot for the I and then this extra dot for the time derivative. So I tend to make that time derivative dot just like a little extra bold. But that's the gist of an inductor. And now, to show how this works in the circuit I showed you earlier, we're going to apply Kirchhoff's loop rule on this circuit. And let's draw the schematic first. Okay, I'm going to put in a source voltage, plus minus. I'm going to provide this source voltage from my Arduino. And then we're going to run this through a resistor, R. And then we're going to connect that in series to an inductor. So it's just that coiled up wire. And then that's next going to go to our capacitor. And then we just bring this back around to complete the circuit. So that's C for the capacitor. And if you're wondering why we call this an RLC circuit, boom, RLC. And there's different configurations for these circuits and they have different utilities. Like if you pull up RLC circuit on Wikipedia, you're going to see these figures. Oops. Oh no. Oh, here we go. So you can put different configurations, like here the capacitor and the resistor are in parallel. Here everything's in series, and this is the circuit we're analyzing. It doesn't matter the order in which you put these. Like in my circuit, I put the resistor first, and then the inductor, the capacitor. The order doesn't matter. So if you want a little read about what these circuits are used for, the Wikipedia page is honestly really great. It's used for a lot of filters. This one is used as a low-pass filter. And we're going to cover low-pass filters in this class. So more to come on that. All right, let's define a current. I'm just going to choose this way. And for the sake of the loop rule that we're going to use, I'm just going to define some points on here. A, B, C. So I'm just defining a point in between each element. So between the capacitor and the source voltage, between the source voltage and the resistor, between the resistor and the inductor, and so on. So let's use the loop rule. The loop rule simply states this. If you sum up the voltage rises and drops going around a loop, it should add up to 0. So I'm going to do this loop. I'm going to go from A to B to C to D back to A. So if I go from A to B, and then if I go across the resistor from B to C, across the inductor from C to D, and then across the capacitor from D to A, all of those voltage rises and drops should add up to 0. So then the next thing is we fill in that next level of detail based on, our voltage rise and drops definitions. So I'm going from the minus to the positive terminal of the source voltage, so I get a voltage rise. I'm going to go across the resistor in the same direction as the current, so that's defined as this. That's called Ohm's law. The resistance times the current, that's the voltage drop across the resistor. And then this one from C to D across the inductor, I'm just going to call it minus VL. And then when I go across the capacitor from D to A, minus VC. And I'm just going to leave it like that. Let's call this equation 1. And next, I'm going to do the element or constitutive equations for capacitor and the inductor. So if you go back down memory lane, the time derivative of the voltage drop across the capacitor is 1 over C times the current. Let's call this equation 2. And then we're going to use our brand new element equation for the inductor. And I'm going to use this dot notation. So I dot is 1 over L VL. And let's call this equation 3. All right, so now we're going to do a little bit of manipulation and play around with these 3 equations. I'm going to combine everything into one second order differential equation. So let me show you how I'm going to do this. First, I'm going to take our second equation, I'm going to take the time derivative of it. And you'll see why I do this in a second. So this now becomes the second time derivative, because I took one more time derivative of the voltage across the capacitor. That's going to be 1 over C I dot. Do you see where I'm going with this? Because we have an equation for I dot from equation 3. So I'm going to sub 3 into the time derivative of 2. So VC double dot equals 1 over C times the time derivative of I, which is 1 over LVL. So what I'm going to do, I'm just going to call this 1 over LC VL. All right. And next what I'm going to do, I'm going to take equation 1 and I'm going to solve for VL so that I can substitute VL in there. So that's easy to do. I can just bring VL over to the right. And so it's VS minus RI minus VC. Okay. So let's sub this into the time derivative of 2. So that means VC double dot is 1 over LC times VL, and we found that to be VS minus RI minus VC. Now what I want is a differential equation that results the capacitor voltage and its derivatives to the source voltage. And so I want to get rid of this current term, and I want to write it in terms of VC. Well, from equation 2, I is equal to C times VC dot. So that's just from 2. And I'm going to substitute that in, and then we're going to be done. We're going to have our second order equation. It's going to be beautiful. So VC double dot is 1 over LC VS minus RC VC dot minus VC. And now I'm going to bring all of the VC terms over to the left. VC double dot plus RC over LC VC dot. So that's just R over L plus 1 over LC VC and we did it, guys. That is the second order differential equation that describes the dynamics of this circuit. Well, it tells us what's going to happen to that voltage across the capacitor as we play around with that source voltage. Okay, so the way we've been learning to analyze differential equations is the first step is you get what's called the characteristic equation, and it's the roots of the characteristic equation that tell you a lot about the dynamics of the system. So let's do that. So I got some questions on homework 3, or homework 4, sorry. For the very last problem, problem 3, how do you get the characteristic equation? Well, you get the characteristic equation for any order system. Could be second order, third order, fourth order, 50 order. You get them the same way. So I'll go about, we'll do this the long way. What you do is you look at the homogeneous part of the differential equation. So that's just VC double dot plus R over L VC dot plus 1 over LC VC equals 0. So the homogeneous part just means you take any forcing function, so in this case, like the source voltage, you set it equal to 0. So it's basically you gather all the dependent variables onto the left-hand side. So VC, in this case, is the dependent variable and its derivatives. You set the forcing function equal to 0. And then the general form for any homogeneous system is going to be A, so some coefficient E to the lambda t. Actually, I should have put like some sub h on this, I guess, to be clear. This is the homogeneous part of the equation. And you know, this would imply that the time derivative is lambda AE to the lambda t. The second time derivative is lambda squared AE to the lambda t. And you substitute in, so you sub into the homogeneous part. So we're going to get lambda squared AE to the lambda t plus R over L lambda AE to the lambda t plus 1 over LC AE to the lambda t equals 0. And you'll notice all of these terms have AE to the lambda t in common. So you can just divide both sides by that. And you're left with your characteristic equation. It's just a polynomial in terms of lambda. That's our characteristic equation. So you can see it's second order, so we're going to have two roots. This circuit is interesting because depending on the resistance, inductance, capacitance, whatever, you can get the whole gambit of different types of roots, which we'll see on the next page. But let's solve for the roots here using the quadratic formula. So we're going to have minus R over L plus or minus the square root R over L squared minus 4 over LC, all of that over 2. And let's just break this into two distinct pieces here. So these are my two roots, lambda 1 and 2. Okay. So not too crazy, right? Just take it step by step. Okay. What I want to do, I want to look at this part of the root. I want to analyze this system from the perspective of the resistance. So we'll run like an experiment and see like how the resistance changes the behavior here. But if you look at this, you can see that this number underneath the square root has the potential to become a negative number. And then you'd be taking the square root of a negative, and then this root has an imaginary part. And that would mean that your system is going to have oscillations in its response. So, let's see here. Let's look at that. Let's take R over L squared minus 4 over LC. If this is greater than 0, hey UB math prof, how you doing? Okay, if this is the case, I want you to look at this table down here. So let's say we have this condition being met. What type of system are we going to have? And I mean in terms of this classification in the second column. Or I guess that's the third column. Ouch, my brain is dead. But I like your live. Don't let your brain be dead yet. We're just getting started. Are you guys alive out there? Are you awake? Whew. Jumping in with the all caps. Oh, I'm pretty sure brain death is the leading cause of actual death. I do think that if your brain has died, the rest of your body won't be doing very well either. Hey Chris, how are you doing? MJ. You're correct. Well, if it's greater than 0, then we're going to have 2 distinct real roots. So it's just going to be overdamped. Good to see you too, Chris. And then, this is the more interesting case in my opinion. If you take that quantity under the square root, if it's less than 0, then you're going to have a pair of complex roots, complex conjugate roots, and we call this an underdamped system. Okay. So if you take these, if you solve for R, because we're going to play around with resistance value today, we're going to see that for an RLC circuit, if I choose my resistor to have a value that's greater than the square root of 4 times my inductance over C, I'm going to have an overdamped system. And if I set R precisely equal to 4L over C, it'll be critically damped. And if I set it to less than that, you guessed it, it's going to be underdamped. Okay, let's start to do an experiment. Let's start to do an experiment. So we're going to take this circuit. Let's see here. Zoom in on, okay. Capacitor. This is 1 millifarad. This is an inductor. I know it looks like a resistor. This is an inductor. It's 47 millihenries. The units of inductance are henries. No idea why. And you might be asking yourself, hey, you said this is an RLC circuit. Where is the resistor? I just see the capacitor and the inductor. Okay, well, it turns out inductors always have some resistance to them. So it turns out this has a resistance of 34 ohms. It is an Arduino. Tox Gaming Geek. Yeah, it's an Arduino. It's an Arduino Mega. Actually, it's an Elegoo Mega, which is a knockoff brand. So we're going to analyze this. Let's write down some stats. Let's draw our schematic again. RLC, and then you got your source voltage over here. And like I said, in the actual system, this is our inductor, because it has some resistance and inductance built into the same actual piece. Circuit diagrams. And there's our capacitor. So this is going to be 34 ohms. This should be, let me just make sure I got this right. Yeah, 4.7 millihenries. And then this one is 1 millifarad. So what I want to do first is, we have a theoretical model for how this circuit should behave. Before we turn this circuit on, I want to take a guess at what type of system it is, so that we know what to expect. I haven't run this circuit yet myself, so you're going to be just as surprised as I am at how it actually works. Okay. Well, how about make prediction, run experiment, assess accuracy of prediction? That's the perfect summary of what we're going to do. Okay. So we developed some criteria for, do we expect this to be overdamped, underdamped, whatever. Let's calculate this. The square root of 4L over C, and then we'll see how our resistance compares to that. We're going to go over to MATLAB. Okay, so R was 34 ohms, I think. I used a little multimeter. I used this guy, you can see if you turn this blah, 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 all the way over to here, it's got this ohm symbol, and you can measure the resistance of something using these probes. So that's what I did. That's how I got 34 ohms. So depending on how accurate this guy was, I don't really know. So that's the resistance of the inductor. The inductance was 4.7 millihenries. So that's 4.7 times 10 to the minus 3 henries. How'd you make that ohm symbol? And then C is 1 millifarad. So 1 times... Oh, wait. L should be times to the minus 3 for milli. And then our capacitance is 1 times 10 to minus 3. 1 millifarad. How are you guys doing that? I guess I can copy and paste. Okay, beautiful. I'm going to throw a little Lil Z in the chat because of that. Beautiful. Everybody throw an ohm. Okay, let's go, because I forgot what I wanted to calculate. Okay, we need to see what the square root of 4L over C is. And if our resistance is larger than that, we are overdamped. If it's less, we're underdamped. Square root 4 times L divided by C. 4.3359. Okay. Whoa, you triple ohmed? Careful, Chris. Okay. So what do we expect to see? Um, 4L over C was 4.3359. And R is 34 ohms. Therefore, R is greater than 4L over C. This means this RLC circuit should be overdamped. What does an overdamped system response look like? Is that ohm cube? Oh, I see what you did there. How about we solve for the roots of this system and predict what the settling time is going to be. And then let's run the actual circuit and see if the settling time matches. Okay. So these are the roots. Actually, you know what? We're going to have MATLAB do the work for us. This is our characteristic equation that I'm pasting. And now I'm going to go into MATLAB, grab the roots. One R divided by L, 1 divided by L times C. Okay. So one root is minus 7,204.5. And the other root is minus 29.5. Is this system stable or unstable? That's a good thing to check before you turn anything on. Actually, let's do it this way. Let's say lambda 1 is that. Lambda 2. What's the time constant of this system? Well, number one, answer my first question. Based on the roots of the characteristic equation, is it a stable system? And how do you assess if that's the case? Okay, MJ says stable. Why do you say stable? Negative roots. Well, you got to be more specific though. It's if the real part of the root is negative. So, I mean, we only have real roots in this case. But yes, because they're negative, they're stable. Okay, follow-up question. So we know that if we turn on this circuit, it's not going to explode in our face. What's the time constant? How fast is this system? Four times lambda 2 fancy U. I don't think that's right. You're onto something with lambda 2. So we know the time constant by definition is minus 1 over the real part of the root, 1 divided by lambda 2. Okay, good. So this system has two roots, but we pick the time constant based on the slowest root. The slowest root is the least negative root, so minus 29.5 is... Wait, I'm confusing myself. But it is lambda 2. 1 over 29.5 seconds. So this is the time it takes for the capacitor to fill up or discharge 63.2% of its capacity. So that's the physical meaning of the time constant. Time it takes for capacitor to discharge 63.2%. The settling time, which is how much time it takes to discharge 98%. Fancy Hubie math process is what I meant. Gotcha. Oh yeah, you were thinking of settling time, which is 4 tau. So that'll be 4 over 29.5 seconds. We'll see what MATLAB has to say. 1356 seconds. Beautiful. Shall we test it? I'm just setting up this circuit here. We need our handy dandy USB cable. I highly suggest getting your own Arduino. There are so many projects you can do with this that are more fun than this, by the way. This is more an educational project, but like for example, a project that I want to do, I don't know if I already told you guys about this. I'm gonna build a cooler that follows you around. Wait, maybe I'll show you real quick. Did I show you guys this? What are you using your Arduino for? Arduino cooler GPS. It just follows your phone. Oh, for GameCube controller input viewer.
Hey guys, this is our autonomous phone.
Yeah, so you can use Arduino for stuff like this. Will it make it in? Boom, no. Okay. Anyways, that's just a little pitch for Arduino. I'm gonna build that in the coming weeks. If I finish it, I'll show it to you guys. Okay, this is the same Arduino code I used for the RC circuit. So hopefully it'll work. Let's suppress that for now. Let's upload this to our board. So this is what they use for autonomous food delivery. Yes, you certainly could. Okay, let's see. Well, you know what? I should change the amount of time. Switch time. So see, I have this variable switch time, which is how much time I take before I turn on and off the power. I don't think we need 10 seconds. I'm going to change it to 1 second. Okay. Now let's watch this. Okay, so the blue is our source voltage. It's kind of just turning on and off, and it has this little dip in it. I'm not totally sure what's up with that. But the red is the voltage across the capacitor. And we predicted that it charges or discharges in a little over 1/10 of a second, I believe. So let's record some numbers. We'll go to the serial monitor. Maybe we can just like investigate here. So the column on the left is the time. The column in the middle is the source voltage. And the third column is the capacitor voltage. So this is when it's already charged up to 1 volt. And now we turned off our source voltage here. It went down to 0.08, and the capacitor voltage is starting to drain. You can see it dropping. And I want to see how long it takes to get down to 0.02. It took like 0.27 seconds, like a quarter of a second it looks like. Let's see when it charges up. So it was discharged here. Let's see how long it takes to charge up to get to 0.98. Okay, so it started at 2 seconds here, so it took like 0.3 seconds. Interesting. So we predicted that our system would be about 2 times faster than that, it looks like. We are off. In recent news, autonomous cooler crashes on highway carrying case of beer. Coolers being investigated for DUI charges. I guess. It would be, wouldn't it? Okay, let me ask you guys, why do you think that we have predicted the system to be a lot faster? And I think it might be the same reason as last time, if you remember. Why do you think we predicted this circuit to be so much faster to fill up this capacitor than what actually happened? Interior resistances are not accounted for. Yeah, I think you're right, MJ. Like if you see this little teal wire that connects the inductor to the capacitor, and once again it connects the capacitor to the ground, and this orange wire is what we're reading the capacitor voltage with. But look at this, the current has to travel all the way to the Arduino. And this wire has some resistance. Oh, and by the way, the source voltage has to travel through this red wire all the way over to our circuit. So I think there's, temperature, material variations. And don't forget, I measured the resistance of this inductor myself, and who knows how reliable that measurement is. Plus, I bought this inductor from Amazon, and you'll notice on here plus or minus 10% uncertainty in the inductance. So we don't even know if it's exactly 4.7 millihenries. It could be 10% under or over. So just a little bit of just real life considerations. Just something to keep in mind whenever you model something. Probably not going to behave exactly the way you expected. Oh, so what I wanted to do was build the Root Locus for this system. And what I'm curious about is what resistance I would need to make this system underdamped. Well, actually, we already know that. The resistance just has to be less than this. Well, let's build the root locus anyway. It'll show us, as we change our resistance, what kind of system behavior we can get. It's good practice. So what I want to do, I'm going to modify this characteristic equation a little bit to prepare us for generating a root locus. So our goal, look at how roots change with the parameter R. Why does the music sound like Final Fantasy VII? I don't know what you're talking about, Phil. It's certainly not. It's definitely not. Definitely not Final Fantasy VII. Okay. So this is our characteristic equation. And I'm going to multiply everything by L. And that's going to allow me to get this R parameter by itself. Now remember, when we make the root locus, we want to make what we call the D polynomial and the N polynomial. So in other words, we want to create d lambda plus r times n lambda equals 0. So if we just match this up with this equation up above, we see that d lambda would be L lambda squared plus 1 over c plus r, and then n lambda is just lambda. So when we go over to MATLAB and we make D and N, we're going to say D is equal to L times lambda squared plus 0 times lambda plus 1 over c times lambda to the 0. And N is going to be 1 times lambda plus 0 times lambda to the 0. So when you're making these polynomials, the rightmost element is always with respect to lambda to the 0, and then it just increases as you go to the left. Hypothesis 2 imaginary branches. Okay, okay. I trust you, Chris. So we're going to have D is equal to L, 0, 1 divided by C. N is equal to 1, 0. And then this is how we make the root locus. You use the command rlocus, and then you just go N and D. Done. Let's make this bigger. Ooh, we do have 2 branches. Okay, now when I click on a point on here, it's going to give me a value, the gain. And because we built this polynomial to be with respect to the resistance, this gain is the resistance value. So this is saying, if I want this like complex conjugate pole, which would make my system have some oscillations, it would be underdamped, I would need a resistance of 3.36. If my resistance was equal to 0, way out here, this is what my poles would be. Well, pole, when it says pole, that's just your system roots. So the roots are purely imaginary out here. And once we get the resistance equal to 4.34, then we have critical damping, where we have repeated real roots. So the blue root and the green root converged here on the real axis, and there's two roots that coincide right there. So like if we go back here, when the resistance is equal to 4.34, that's the critical damping that we solved for. And it's the barrier between being overdamped and being underdamped. So we're seeing the root locus give us that same result. Now, we had an overdamped case. Let's see, we had one root that was at minus 7,000, right? And another root that was at minus 30. I'm going to try to find that over here. Maybe like here. Let's move it. Yeah, when you have a root at minus 30, the resistance is equal to 32. So this is kind of where our resistance was. And it seems like the resistance is even a little bit more in real life. So maybe, I don't know, maybe it's closer to 40. And that would make our system a little bit slower. Because the closer you get to that imaginary axis, the slower your roots get. Okay, another quiz question, and then we're going to take a break right after this. What resistance do I choose so that the capacitor charges as fast as possible? .34. Why do you say that, MJ? Does everybody else agree? Can we check the settling time with the serial monitor? We can. We did a rough check. It was right around 0.3 seconds. Chris. Right here is where the resistance is 4.34, and this is the fastest possible settling time because it gets both roots. It's where you have two real roots that are repeated, making the system critically damped. Good. I think the best way to explain it is you look at this blue root. When the resistance is 0, it's right on the imaginary axis, which is as slow as this system can possibly get because it has like no damping. As you increase the resistance, this blue root moves farther from the imaginary axis, and that makes it a faster root. So it's getting faster, 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 and then once you get here, this is as fast as it's ever going to get. Because if you keep increasing the resistance, then it starts working its way back this way, and it's getting slower and slower and slower. So the resistance we had made our system pretty darn slow. But that's the resistance built into the inductor, and we can't really do anything about it. So as far as this real life system goes, that's as fast as we're going to get. Why have we only been analyzing the resistance in the circuit? I just kind of picked it. We could analyze other things. We could look at the inductance. What are you interested in, MJ? Will the time it takes for the break-in and breakout points be equivalent to hit the critically damped point? That question confuses me. For the break-in and break... Are you just talking about the two roots? Yeah, at the critically damped point, I guess the two roots are equally fast. Put a potentiometer so you can change the resistance of the circuit live. Oh yeah, we could do that as well. All right, everybody. We are going to take a 5-minute break. We're going to resume at 3:25 p.m. Eastern. And we're going to start talking about the step response of a second order system. All right, so take a 5-minute break. We'll be back here at 3:25. I think what I mean is one is traveling first on the real and one is imaginary. So how can we tell the time? Wait, both roots start imaginary. Like the green root starts down here, the blue root starts down here. I mean up here. And as you increase the resistance, they symmetrically move with each other until they reach this point. So they're both imaginary at the same time, they break in at the same time, and then they're real at the same time. No problem. I'll be right back. little iced coffee. It's really hitting the spot. Has anybody played the Final Fantasy VII Remake? I got it, but I haven't put too much time into it yet. PS4. Check your email. What did you do? No, I'm just, I was playing with you, Phil. I'm aware of what I've done. I'm aware it's Final Fantasy VII. I love that game. Okay, guys. If you're following along with the handout, we're starting to look at the step response of a second order system. But I actually want to skip this page first and go to this page. So we're going to go to the last page. We're going to go through the steps of solving this differential equation. And then we're going to go back to the previous page and unpack how this works, or what it looks like when you graph it. Okay. So I'm going to start. Okay. So let's break this down real nice. X of t, it's going to be a combination of a homogeneous part and a particular part. And I want to start with the particular part of the solution. That's how I like to start these problems. Now, the rule of thumb with particular solutions is that their form is equal to the same form as the forcing function. So I'll just write that. Our forcing function is this. And I just want this to be a constant number, A. So it could be 1, it could be 2, it could be 3, but it's going to be that number fixed for all time. So constant in this case. So I'm going to say x particular is equal to some constant d. It's not necessarily going to be the same constant as the forcing function itself. All right, so that's why I put a different constant. So maybe I'll put that in parentheses. So D is a constant. And then we're going to sub this into the particular part of the differential equation. So maybe I'll, I think I've done this before, but it might be worth it to break it down really nice again. If I substitute this whole thing into the differential equation, you're going to have x homogeneous t plus x particular t oh, I meant a different color. The reason I'm doing this is it'll explicitly show you what I mean by the particular part of the differential equation and the homogeneous part. I think my tablet's starting to heat up. I can hear the fan just whining in protest. So I'm going to put this forcing function A in purple because it belongs to the particular part of the differential equation. And then I'm going to put a plus 0. All right. So now we're going to have I'm going to separate out these two pieces. So this is the particular part. And then this is the homogeneous part. So when I say we're going to substitute this particular part into the particular part of the differential equation, it's this purple part that I'm referring to. So what I'm going to end up with, because the time derivatives of the particular solution are 0, I'm going to have omega n squared times my particular solution, which I know is a constant, is equal to A. So that means D is A divided by omega n squared. And this is my particular solution. Okay. So, easy peasy. The particular solution is the easiest part. Let's do the homogeneous. So the first step is get the characteristic equation. I'm going to skip some steps. That's what you're going to get. And the roots, if the system is underdamped, these are going to be your two roots. And we can make this a little easier if we just substitute the damped natural frequency in there. And we know that for complex conjugate roots like this, the general form of the homogeneous solution it's going to be e to the real part times t. And then we're going to have a1 cosine omega dt plus a2 sine omega dt. So this means I'm just going to copy this. X of t is the homogeneous part plus the particular part. And all that's left is to solve for A1 and A2 using the initial conditions of the problem. The initial conditions for this were that that x is 0 at time equals 0, and also x dot, the time derivative of x, is 0. That's like the standard initial conditions for what we call the step response. Okay. So, x of 0 equals 0. So if I plug in time equals 0 everywhere, I'm going to get a1 plus a over omega n squared. So that means this coefficient a1 is minus a over omega n squared. And remember, a is just the amplitude of the step input to our system. I'm going to box this. All right. This is always the longest step, taking the time derivative of this blasted thing. Don't forget the product rule. Whenever I get to that part, I just feel tired knowing that it's coming up, taking the derivative of that ridiculous function. Okay, so we're saying that equals 0. So if I plug in 0 for time everywhere, only the cosine terms are going to remain. And I think this is all we're left with. You know, this is going to go away. That's going to go away. These terms go to 1. This goes to 1. This goes to 1. Alright, so A2 is zeta omega n A1 over omega d. And we know what A1 is. And omega d I'm just trying to simplify this a little bit. I believe that's right. Whew. And you know what? We're not even going to write out the whole thing. You can write it out if you want. But you have to plug in A1 and A2 into this up here. And that is the equation for the underdamped step response. So what happens is, like, just looking at this function, you can kind of already get an idea for what it's going to look like. There's going to be some oscillations that come from the cosine and the sine. Those are going to exponentially decay until they go away. But the system is going to approach a final value as t goes to infinity, and that final value is going to be a over omega n squared. Speak French, no English, only English. I'll carry on in English then. Okay. Let's go look at the graph of these step responses as a function of the damping ratio. So they say c of t here. Let's just call it x of t because that's what we solved for. They normalized this so that the final value always goes to 1. And notice, each of these lines is different in that the damping ratio is changing. So when the damping ratio is 0, we call this undamped. which means that the oscillations never decay. And you can see that here. We have this peak value here, and then when we get to the next peak, it's still at the same place. So a damping ratio of 0 is just sustained oscillations. If you increase the damping ratio to 0.1, well then it decays with time. Can this be related to transmissibility? It certainly can. Transmissibility is, we use it in different things, but it's how much force or vibration is transmitted from one body to another. So that's important for a problem like vibration suppression. So you see that as we increase the damping ratio, the peaks drop off in amplitude faster and faster. And we know that once the damping ratio becomes 1, this is called critical damping. And generally, this results in the fastest possible settling time. If you look at all these responses, they settle in different amounts of time. Settling is how quickly you approach the final value of 1. Fastest settling time. And then once you go greater than 1, we know that we are overdamped. So anything above 1 is an overdamped system. So the Rlc circuit we built today, overdamped. And then all of these guys, 0.1, 0.2, 0.3, 0.4, underdamped. Okay, the last thing we're going to do today, then we're done. We have a little bit of vocabulary that helps us to compare these responses a little bit more. So I made a little table. Settling time. We already know. The definition we're using is the plus or minus 2% settling time. So time it takes to get 98% closer to your final value. So it could be you're ramping up to some value or you're discharging to some value. So here in this is their settling time. It's the time it takes the envelope to reach that threshold. So maybe we should specify that. So the envelope function. Okay, so you guys already knew that one. Let's do rise time. Let's talk about, there's different definitions for this one. We'll do the definition of the 0 to 100% rise time. Or actually, let's just put both, because this one is the one shown in the figure. They also do the 10% to 90% rise time. So if you look down here, we have the function getting to 10% of its final value and then getting to 90% of its final value. And if you look at how much time elapsed in between there, that's the rise time. Or the 0 to 100% is just the time it takes for it to first meet what's going to become its final value. And it's not based on the envelope, it's based on the function itself. So, if we define it, the time it takes for the function itself and let's use this 0 to 100%. From 0 to the first time it intersects its final value. So that's the 0 to 100%. To go from 0 all the way to the very first time it intersects its final value. Okay, 2 more, and then we're done. The peak time, that's T sub P here on the graph. Simple enough. Time to go from 0 to the first peak. So obviously this only applies to underdamped systems. Only an underdamped system is going to have this peak and then some oscillation to bring it back. So maybe we'll put that here. Okay, the percent overshoot. That's right here. So this is the percent of final value by which the first peak, percent of final value by which the first peak. Oh man, I'm having trouble putting this one into words. Maybe we'll just say rises above. So maybe this one in the figure looks like about 25% overshoot. Because it goes to, let's say it goes up to 1.25. So that's some vocab for the step response of a second order underdamped system. Whew. We blasted through a lot of math in this second half of the course. I feel a little drained. I bet you do as well. Guys, we're going to leave it there for today. I'm going to hang around if any of you have questions. But thank you for your attention. Thank you for your participation. I'm having a lot of fun doing this summer class with you guys, so I appreciate you. I hope you have a great weekend. I hope you get some rest, some relaxation, maybe some exercise. If there are no class-related questions, I would love to discuss the inverted pendulum. We can discuss the inverted pendulum. If you don't know what Chris is talking about, chances of on-campus classes for the fall. You know, the last that I heard, they were supposed to give us some more information on June 1st, but now it's June 5th. And I haven't heard anything new. My suspicion tells me it's going to be some like mix. Like, I don't think we'll be back 100% to where we were. But I would guess we're back on campus. Yeah, I wish I had more info for you, sorry. Yeah, if you're curious, have a good weekend, you too, Kevin. The stuff we do in this dynamics course, it's the prerequisite for doing this kind of control system stuff. So you just gotta fight through dynamic systems and then you can do really fun stuff like this. So, I'm wondering if we make our own body components. Yeah, I think so. Like they 3D printed this arm and stuff, and then they machined this disc. I can't remember what they made it out of, if it was steel or aluminum. But yeah, I think we would make our own body components. Maybe just make it out of wood? I don't know. He's not really hitting that thing. He doesn't care. Oh yeah, see, they CNC'd that whole thing. They're in Argentina. Ooh. I think they swing this at the natural frequency of the pendulum. There it goes. I know that the rotational speed and resistance can change greatly with the mass and placement of spokes. Yeah, do they talk about... Where are you? Not really in depth. Yeah, like this graph is kind of cool. They're saying depending on how long the pendulum arm is, you can tip the pendulum over further. Like, I guess, so if it's a shorter arm, like 0.15 meters, you can tip it over 45 degrees and it'll be able to correct itself. But if you make it longer, you can only go like 20 degrees. Yeah, I guess they don't talk too much about how they specifically chose to put the spokes in this configuration. Oh yeah. No, I think they... It's not an easy read, but they do a really nice job. This is interesting to look at, like, their simulated system has no oscillations, but the experimental does. So it's showing that they predict the closed loop system roots to be somewhere that they are not in reality. Which is the same thing we ran into in digital controls. Is the office hours also on this live cast? Yes. That's what we've been doing so far. So every weekday, so even on Tuesdays and Thursdays, I'm here from 4 to 5 p.m. Eastern to take any questions. So if you have any questions, you just throw it in the chat. We discuss. I see. I can't get to lecture when we have it, so I watch the recorded ones. Oh, gotcha. No problem. Yeah, if you can ever make it between 4 and 5, I'll be here. Can I ask about number 3 on the homework we just turned in? I was emailing you with the questions. Sure. It's going well, UB math prof. I know emails 20 minutes before it's due is not ideal. Oh, it's all right. It's all right. You weren't the only one. I was getting a couple emails this afternoon. Is there a particular? I'll pull up that homework. Is there a particular one you want to see? Specifically about how you extract K and the other values from the third order equation. Sure. Let's do it. Chris says, I'm going to model this in Fusion so we can use the workshop. I have a fabrication shop at my disposal, but I'm not sure how exact I can make a wheel at the shop. Ooh. Well, it doesn't have to be perfect. Okay, let's take... Let's take this one. Let's take this one. So, the first step is to get the characteristic equation. How do you feel about getting the characteristic equation? Are you comfortable with that? This is the characteristic equation. I struggled hard with that. Sucks because you can't... Oh, too much. Yeah, I hear you. So, the way you get the characteristic equation is... We know that the homogeneous solution has a general form that looks like this. AE to the lambda t. So the way you get the homogeneous solution is you substitute this into that homogeneous form of the differential equation. So the homogeneous form is just with the right hand side equals 0. So if I want to substitute this in, I have to have all these extra derivative terms. Because this goes all the way up to the third order. So the third order term is this. So then I just substitute these into that equation. So like the third derivative was this, plus 9 times second derivative plus 28 times the first derivative plus k plus 20 times the 0th derivative. Oops. So, you notice I can divide everything by AE lambda t. And then you're left with just this, a polynomial in terms of lambda. Does that make sense to you? Oh, you were good up to this point. Ah. You could have stopped me, bro. Okay. So the next part is I want to put this in a form that looks like this. Sorry. No. I'm just playing with you. Okay. So in lambda is the polynomial that is multiplied directly with k. Well, I mean, in this case, k K is just being multiplied by 1 effectively. It's not being multiplied by lambda or anything. So n lambda is just 1. And d lambda is all the stuff that isn't multiplied with k. So it's lambda cubed plus 9 lambda squared plus 28 lambda plus 20. So this is d lambda. This is n lambda. And k is k. So you can have an n lambda that is not at all a function of lambda. Yes, actually, yeah. Well, think about it this way. In lambda is a polynomial in lambda generally, but a polynomial always has, or you can always take it to a 0th order term. So just like d lambda has 20 isn't being multiplied by lambda. I see what you're saying. It's like you're calling this a function of lambda, but it's just a scalar constant number that's not being multiplied with lambda. But this is just saying generally it can be a function of lambda. Oh, that's what's holding me up. I was convinced there had to be a lambda expression in the variable. No. No, you don't need that. Ooh. Okay, great. After this, you just plug these expressions into MATLAB and read the graph. Yeah, so in MATLAB, this one would be 1, 9, 28, lambda squared, lambda. Yeah. And then n would be, I think you might have to do this. Or maybe you could just put 1. One, 9, 28, 20. I'm just gonna try 1. Yeah. If I make n I think I'll get the same thing. Yeah, same thing. Good. This one is a little bit tricky when predicting the fastest settling time. Because these two roots, the blue and the green one, as you increase the value of k, they get slower and slower and slower. But this red root, as you increase k, it gets faster and faster and faster. So the place with the fastest settling time would be when all of these roots line up. Yeah. I don't see why the red part gets faster and faster as you increase K. Can you explain that? Yeah. So, actually, I'll go over here. So, when I'm saying a root is fast, that comes from the homogeneous part of a solution is like some constant times e to the root times t. Oh wow, I got that part wrong. So, you know, this, it'll be exponential decay, and the time constant describes like how quickly it decays. So the time constant is -1 over the real part of the root in general. So a small time constant means fast decay. Well, how do we make this time constant small? If the magnitude of the root, or if the magnitude of the real part of the root because if you divide by a big number, then the time constant becomes smaller. So I want this number to be really big. So what that means in terms of the root locus, if I move this root more and more to the left, you can look at the number on the real axis. It's going to -8, it's going to -10. And the bigger I make that number, -12, -15, the time constant is getting faster and faster and faster. But you take this blue root, I'm coming this way, the numbers, the closer I get to this imaginary axis, the real part of my root is very small. It's getting closer to 0, and it's getting slower and slower. The time constant's getting larger. So a root that has a more and more negative real part is a faster root. Nice. Chris says, can you send me the dimensions of a DC motor you have laying around? I can make the components if I have the dimensions of the spindle and motor diameter. I think once we have the base and arm, I can make a few different wheels to see what works better. Let's see. The motor I have... But I don't know if this is the motor we'd want to use. this guy. Actually has an RC car wheel on it right now. What motor? I think they used a 12 volt. Motor. Because, Chris, they chose their motor after doing some analysis. Because you have to know how much torque the motor has to produce and all that. .24 volt, 7 amp, brushed. Maybe we can do 24 volt brushed DC motor. What RPM? It can get up to at least 9 revolutions per second, which is over 500 RPM. There are a ton of factors in this analysis. It seems your line of thought is trying to match the output. Because, well, they point out two important things. You want a high torque motor that has a high top speed as well. $12 amps. Torque 2 kilograms. I don't really know what that means. Kilograms is not a torque. I was checking my code on the problem we just did. I typed the same thing and didn't get the same graph. Are you sure it's the same thing? Your code looks just like this? D equals 192820. N equals 010. Oh, no. If you do 010, that's different. If you look at my N, I did 1. Or I did 0, 1. But this means that the 0th order term, yeah. If you do 010, that's like multiplying k by lambda. $10,000 RPM. The motor's starting current needs to be 10 amps. which component will be the most expensive out of the bunch? I think the motor will probably be $30 or something. Actually, we should get a motor with an encoder to measure the angle, obviously. The motor driver is probably like also between 20 and $30. I don't know. Maybe the most expensive thing is machining the reaction wheel. Like if it has to be CNC'd to get it really precise. No, I can do that cheap or use the school's equipment. Oh, I see. It's probably the motor. They did a custom gearbox for their motor. That's kind of cool. Based on simulation, they found it would have the highest recovery angle with a gear ratio of like 10. What gear ratio are they referring to? I think it's from the motor output shaft to the shaft that goes to the reaction wheel. Like if you look, yeah, I think there's a gearbox. Like here's the motor shaft in there, and then I think there's a gearbox over here. That'll definitely take a little CNC work. I wonder if you can buy these gearboxes. I don't know. Sorry, I'm loving the shop talk right now, but one last question on that problem. The part about which values make the system stable. So, stability has to do with the real part of the root. So, like this one, Chris, I'm super jealous you have access to a shop. I would not even realize there was a quarantine if I had a shop to work in right now. Yeah, man. So, you see, here's the imaginary axis. If the roots go over here and have a positive real part, then the system is unstable. So that's the definition of stability. If any of the system roots have a positive real part, that results in system instability. So it looks like if the gain, in this case, or the parameter k, is larger than 240, these blue and green roots become unstable. Okay, great. This is what I thought. I keep second guessing what you taught us because I think it might be a trick question. I would never do that. Never. Have I done any trick questions? I haven't done any trick questions. Why would you think it? You made us bet our life on it a few times. That's true. That is true. You've been put in certain situations where you had to take your own life into your hands. But that's what we do every day when we walk out that front door. Your life is decided through your choices. Oh, Chris, I disabled links. You can send, I think you can send direct messages. RPM. Sometimes you just gotta grab life by the characteristic equation. Oh, okay, cool. I like that quote. This will give you an idea of stuff I've fabricated or helped fabricate. Should I look, do I look at fabrication? Whoa. Dang. Chris, you're an artist. Honoring the art of the build. Which one did you work on? It's like riding a donkey without a tire. I work with him when I'm not in school. Great guy. I learned a lot from him. Oh, you were a plumber and GC prior. What's GC? Oh, general contractor. So you know what you're doing. That's awesome. Gotta run. Thanks so much. Hey, thank you. Have a great weekend. You can build anything. Oh, this motor's tiny. I'm just not great with electricity yet. It's my weak point. Yeah. Yeah, my electrical knowledge is... I still want to learn a lot more. Yeah. I mean, electric vehicles are going to take over. Guys, I'm gonna call it a day. Or my first objective is to get some food. Chris, we can keep talking about this pendulum thing. I'm interested in building that. It'll take some work to figure out what motor we should be using, but that's not too bad. Over the weekend, I'll put some time into this. Thank you for your time and knowledge. Have a great weekend. If I see anything relevant, I'll send it your way. Hey, thanks, Chris. You have a great weekend, brother.